In the last chapter, we already encountered some really interesting combinations of gates that serve some very general purposes, such as creating entanglement. Now we start to utilize such combinations to serve some more specific purposes, and we do this in two chapters, one concerning quantum communication and another one concerning quantum computation. In quantum computation, we deal with algorithms that are designed to process information, while in quantum communication, we have protocols that are designed to transmit information from one place to another. So we will start with quantum communication, and then here we are going to look at the following examples. We will look at superdense coding, quantum teleportation, then some protocols for so-called quantum key distribution, and in there we will study two specific examples, the BB84 protocol and the EPR protocol. These are all applications that have been realized in labs or in the wider world, so these are really very practical applications. And all of them highlight some very general features that we are really interested in, such as the role of entanglement and the role of measurements. And to set up our discussion, it is very useful to ask one very specific question about entanglement. In our discussion of entanglement, we encountered the Bell pairs, such as this one, so these maximally entangled states, and these will play a very important role in our examples. And the question that we want to ask is, how easy is it to change one Bell pair into another? So let us have a look what we need to transform this Bell pair, for instance, into the following one. Given here. And then we see that we can achieve this actually in several ways, but all of these ways are actually very simple, maybe much simpler than you would expect, because all of this can be achieved by operating at only one of the two qubits. In particular, we can achieve this by applying the NOT gate, the Pauli X gate, to any of the two qubits. So for instance, when we apply this to the second qubit, we immediately see that this 0 here becomes a 1, and this one becomes a 0. So this definitely works out. And alternatively, if we apply the Pauli X gate to the first qubit, well, then this 0 here becomes a 1, but then we just obtain this state here, and this one becomes a 0, and then we obtain this state over there. And the order of the summation of these states, of course, does not matter, so we achieve the same thing. So even though these states encode information sort of globally across both qubits, we can still manipulate this in a meaningful way by operating on just one qubit at a time. And this then can also be achieved for the other Bell pairs. For instance, this one here, which we can obtain from the first one by applying a Pauli Z gate. And again, we have a choice. We can do this either to the first or to the second qubit. This will simply convert this plus sign into this minus sign here. And finally, we have this Bell pair, and this we can obtain very straightforwardly by applying a NOT operation, a Pauli X gate, to the second qubit, or indeed also to the first qubit, but then with an overall minus sign. But overall signs in front of a state actually do not matter, so we can actually ignore this. In terms of the physical manipulations, this is all that we need. So let us briefly see how this works. Well, this 0 becomes again a 1 when we operate on the second qubit, so this works out straightforwardly. If we operate on the first qubit, then we just interchange again the two states, and then this minus sign appears. But as I said, this does not really matter. It does not affect any physical observable properties of this system. And we can also go this way, where we can apply the Pauli Z gate to the first qubit. So then we obtain a minus sign from here. And again, we can also apply this to the second qubit. Now the minus sign will appear from here at this place. So this is again up to an overall minus sign in front of all of this. So we can use so-called local operations to convert one of the bell pairs into any of the others. In particular, we can also go all the way from the first one to the last one by just applying these gates consecutively. And now this is indeed utilized in the idea of superdense coding. Let me first specify the circuit, and then I will explain the purpose of this. And this is because the circuit is actually very simple. It involves just two qubits, and these are initially prepared in this bell pair here. And then in here we will apply a controlled NOT operation and a Hadamard gate. So part of the circuit just looks like this. And this part here indeed just looks a bit like our entangler circuit, but with the order of the gates interchanged. And so this is actually doing the opposite of the entangler. So starting from this bell pair here, we would just end up in these computational basis states. And running it in the opposite direction, we obtain this bell pair here. So this is the inverse of our entangler circuit. And I'm going to call it the disentangler. Now we add some further elements, but they're actually very simple and serve the purpose to transform our original bell pair into another bell pair at this position. And we can achieve this in the following way. Namely by inserting an X gate and a Z gate at these two positions, but we will use these not all the time, and for this I'm going to introduce a new very simple symbol, namely this symbol here. We say that these double lines are lines of classical communication, and in these two cases they are controlling the application of these gates, so these will not always be applied all the time. They will only be applied if a certain classical bit, which I call M1 or M2, is 1. And in the case that these bits are 0, the corresponding gate will not be applied. So to repeat, we have two single qubit gates inserted at these two positions, but we will not always apply them. We have a choice to apply them or not, and we encode this into these two bits here. And now what we will obtain on this side here will not always be the state here. So we really just have 4 different circuits rolled into one, depending on the values of M1 and M2. And the outputs we can simply put into a little table. So for the case that these two bits are 0, we do not apply these gates here at all. Hence we just run the disentangler on this bell pair and end up in these computational basis states. Now if M1 is 0 but M2 is 1, then we can look at our examples above and we see that at this place we end up in the state beta naught 1. So this is for this specific example here, and now disentangling the state we will obtain the following result. Namely, again, the system comes back to computational basis states, where the second qubit is now in the state 1. In contrast, if we only apply the Z gate, so have this combination of classical bits, then at this place we have the state beta 1 naught, and so our final state is just given by these computational basis states for each of the two qubits. And finally, if we operate with both of these gates in this particular sequence, so first the X gate and then the Z gate, and in both cases just on the first qubit, then we simply end up in this state here. And if we look at all these results, we see that the first qubit always ends up as labeled by M1, and the second qubit always ends up as labeled by M2. So we can summarize all these results by just saying that the first qubit ends up in the state M1 and the second qubit ends up in the state M2. And now, because these are computational basis states, we can read them off immediately by a measurement. And for this, I'm again introducing a specific symbol now. Measurements in the computational basis on a single qubit, we are now going to denote by this symbol here. And we are going to apply this now to both of the qubits. And because here we deal with definite states of information, the results will just be M1 and M2, so there are no probabilities actually for this. This will definitely happen this way. This is already the complete circuit, and what it achieves is actually quite remarkable, because it transforms something that we do on just one of two qubits to something that we can read off by doing measurements on both qubits. That this is something really remarkable we are going to see when we just phrase it in a suitable context. And for this we are going to assume that there are two people, A and B, which conventionally are called Alice and Bob, that at some point got together and created this bell pair here. And then they went their way and took one of the two qubits with them. So here Alice and Bob sort of cooperated to create this bell pair. But now they are separated in space, so operate in different realms. In particular, Alice has access to this qubit here and can now decide, depending on these classical bits M1 and M2, whether she would like to apply these quantum gates X or Z. And then she's going to transfer her quantum bit from her realm or range of influence into Bob's realm. So note that at this point, only a single quantum bit is changing its location. So Bob can then run this disentangler on the complete pair of quantum bits in his possession and do these measurements, by which he obtains complete knowledge of these classical bits M1 and M2. And this he could achieve even though Alice only operated on a single quantum bit, and at a time when Alice and Bob were already well separated. And afterwards only a single quantum bit needed to be transmitted. So 2 bits of information were transmitted, and they are of course stored in 2 quantum bits, but in the essential transmission process only a single quantum bit was involved, so you could say a little bit loosely that this was achieved by just sending 1 quantum bit. So this is superdense coding. It beautifully illustrates the usefulness of entanglement and emphasizes how entanglement leads to information shared globally across a whole quantum system. And it also illustrates how we eventually obtain definite information by doing a measurement. So we end up in definite states of information and there are no probabilities involved. Next, we are going to turn to quantum teleportation. This shares many of the aspects that we just discussed, but serves a different purpose, a purpose which is very interesting indeed.